Hello, can everyone hear me?
Yes.
Okay, great, fantastic. So I think we'll start and then people can join as we go. Hello, everyone. I am Kamen Kozarev from the Institute of Astronomy, the Bulgarian Academy of Sciences, and thank you very much for signing up for this, I'm sure, very interesting and useful course on the introduction to antennas. The course will be taught by David Prinsloo from the ASTRON, the Netherlands Institute for Radio Astronomy. And it is part of the Stellar project, which is a Horizon 2020 project, uniting the Institute of Astronomy, the Technical University of Sofia, ASTRON, and the Dublin Institute of Advanced Studies for exchanging know-how and for enabling the growth of a strong radio astronomy community in Bulgaria. So this is actually the first activity of the project. And I'm really excited. We were able to make this course available to many more people than expected originally. So without further ado, I'd like to introduce Dr. David Prinsloo, who will be teaching the course. He'll give you more information and details about the way this will be done. David?
Thank you, Carmen. Thank you for the introduction. And hi, everyone. My name is David Prinsloo, as it says underneath my image there, and as Carmen just introduced. So just a short background on myself. I'm originally from South Africa, where I continued my, or let's say that my university studies and research into antennas, specifically for radio telescopes. And yeah, through this research, I received a position at the Netherlands Institute for Radio Astronomy, ASTRON, and I've been working there as an antenna researcher now for 5 years. And yeah, part of that is also putting together some course material for various courses I've given at other universities or to people from industry, just to give people a sense of, okay, what are antennas all about? So the intention with this course is it's almost a collection of that course material. And as Carmen has introduced and mentioned, initially it had been planned to be quite a small handful of people almost, somewhere at a location, hopefully ASTRON, or it would have been fantastic if I could have come to Bulgaria to give it to you there in person. But nonetheless, here we are, everyone in their homes or wherever you are. And yeah, it's fantastic. We have nearly 50 people in this course. So I'm curious also to see how this goes in an online setting. And I would also appreciate your feedback on that afterwards. So any comments or feedback would really be appreciated. So, and since this is very much now me talking to a screen, I would really appreciate your interaction as well. So feel free to use the chat at any time. I think you can raise your hand in Zoom as well. I'm not sure if anyone knows how to do that. I think, let's see if I know how to do that.
On the bottom panel, you should see a reactions button, and amongst reactions, you can see a thumbs up and a raised hand and so on.
It's exactly the comments that I want to hear. So, so please feel free to raise your hand, or as Ian just did, please just speak up. So feel free to interrupt me at any time. I will try to keep an eye on the chat, but of course, once I'm busy writing somewhere, my eyes might not be on the chat window. So if you feel that I'm ignoring you for too long, it means I'm not seeing your question. And as far as the course materials will go, I'll be sharing my screen most of the time, but I'll be also making hand notes. And I would like to encourage you to also, especially on the equations, please write that down for yourself, because you'll see that I've not shared the notes with you. And the reason is I want you to first see the work almost for the first time as I present it. I will be sharing the notes with you afterwards. So you'll be using some of the equations later on. So I would really recommend that you write your equations down for you to be used at a later stage. Otherwise, I can always just call them up if you don't have them at hand. And what I'll be using in addition to that is Mentimeter. So this is a website, and I would like to ask you all to quickly do this. In a second. If you could all go to the following website, menti.com. I hope you can all see this. And enter this code when prompted.
Sorry, could you repeat the website? Oh, I see your screen now. Yeah.
Done?
Yeah.
Sorry, do you mind going back to the slide with the code on it?
Yeah, apologies for that. There we go. Some of you can see that. Okay, see, not everyone is on Mentimeter yet. Someone having difficulty with that, or you don't have your smartphones with you. We'll be using this throughout the course, so I'd appreciate it if most of you can log in and attempt this.
Maybe I'll join and just ask in Bulgarian. Някой има ли проблеми с включването към menti.com? Ако да, пишете ми.
Аз не съм сигурен дали съм направил всичко правилно. Попитаме за код, вкарал го и после ме попита каква ми е позицията.
Да, това е.
И... Добре.
Okay, but I see 35 people have managed so far. So 37, okay, more of you getting on. And it'd be good if you can just keep it on your cell phone, keep it on the side, because I'll be using this, as I say, regularly throughout the course. Okay, so it actually seems that the majority of the attendees are in academics, which is interesting to see. I think this was primarily always designed as a course for, let's say, graduate or just undergraduate students as well. But my assumption in this course is as well that since it is an introduction to antennas, I really do assume that you have never worked with an antenna before. So the course material really takes it from the basics, and maybe just to get it for me to also get a sense of what your experience is with antennas. I have a second question that I want to pose to you. So I see. I think that's nearly everyone. So I will close the voting, if that's okay. and move on to the next question. This is just to help me get a sense of how experienced you are in antennas. So have you ever worked with an antenna? Which one of them have you worked with? You can, I think, select more than one option here as well. Okay, great. I'm glad to see at least, nice, 20 at least have never done an antenna. So yeah, dipole, that makes sense. Most people, I think, that have had any introduction to an antenna, that is typically where you'll start with. And that's also exactly where I will start with in this course, is with a dipole antenna. But before we get there, the first part of this course is really for the 21 people among you now that have never done anything with antennas before. So I'm really taking it from the start, and that is to get a sense of what are the fundamental parameters of antennas. So these are the parameters you need to know to be able to assess the performance of an antenna. So this first part will really be definition upon definition upon definition upon definition. So I'm asking you to just bear with me for the first part. You'll see that as soon as we get to the antenna elements during the second part of today, then we'll be continuously referring back to these values. So you have to at least have seen this once. So I'm really glad to see that just under the half of you have actually never worked with antennas before. So yes, this first part is definitely very much for you then. Okay, I'll close this voting again. Close. And move to the course material. Let me just see if I move this away for you. I assume that you can all now see the introduction to antennas slide, correct?
Yep.
Okay. So introducing antennas, you can't really do this without starting, with Maxwell's equations. So obviously to pay homage to James Clerk Maxwell and this mathematical model for exactly applause, mathematical waves published, I have to do the same thing. And this is not really a advanced mathematical or electromagnetics course where we'll be digging into these equations at all. We'll be looking at it more in a qualitative sense. But still, we need to start here. And this is actually where antennas, or the theory of antennas, really started. And this was in the late 1800s, so 1865 to be correct. Maxwell published these equations, and the power of them is that these four equations describe and relate the electric magnetic field, electric magnetic currents. Magnetic currents is not quite a physical quantity, but helps to have them defined with one another and relates them at any point in space and any point in time. And this is a really powerful tool to have, or let's say mathematical model to have. And it's thanks to this model that the entire field of antennas had been started. Now, at the time when he was publishing this, or he had published this, no one actually knew, okay, so we have got this mathematical model for this, and it was almost a bit of now what? So it was only until, well, not long afterwards, Heinrich Hertz in the 1800s, again, really proved and demonstrated Maxwell's theories. And he showed that, okay, these electromagnetic waves predicted by Maxwell, they actually exist. And I think most of you are probably aware of this. His experiment, what he did is he induced a spark in between two copper wires with these zinc balls attached to the ends. Now you can almost start to see the resemblance here to a type of dipole antenna that he had created. And what he noticed was that if he brings a loop close to this, let's call this for the moment, for the lack of a better word, dipole, and there's a gap in this loop antenna, whenever he induced a spark in the dipole, he noticed that a spark was induced in this loop, if the loop was in the vicinity of this dipole antenna. Now, this seems quite simple, but this is an extremely important observation that he had made. And what he had proven through this rather simple experiment was that, first of all, electromagnetic waves propagate at the speed of light. And even more important is that it's possible for electric and magnetic fields to detach themselves from a conducting surface and propagate as waves. And this is exactly what Maxwell's theories modeled. So Heinrich was the first to actually demonstrate this. And ironically enough, as you've probably read now in this quote, is that he said, "I don't think that the wireless waves I have discovered will have any practical application." So yeah, I think we all now know how completely incorrect he had been in that, as I would not have been able to talk to you right now without exactly this. But it was not long afterwards that Guglielmo Marconi, he saw the potential of this. And he said, well, we can commercialize this technology. And he did exactly that. He showed that you could use wireless transmission for communication. And the way that he did that was by this transatlantic experiment. And I think this is quite well known as well. What he achieved was he placed a transmitter in Cornwall, in England, and a receiver in Newfoundland, in Canada. So, and he managed to transmit a single letter, the Morse code letter S, which is just 3 ticks, across the Atlantic Ocean. Yeah, there's also the legend of how he actually received the signal. Here you can see the transmitter station that he had in Cornwall, quite an elaborate construction. And he had a similar receiving station in Newfoundland, which due to a storm apparently got destructed. So he ended up connecting a cable to a kite or a balloon. I think here a kite is shown. And this was his receiving antenna, just a very long cable attached to a kite, dangling in the air, but apparently sufficient and sensitive enough to detect the Morse code letter S transmitted from the other side of the Atlantic Ocean. And it's thanks to this successful demonstration that the wireless revolution really started. But the one thing, well, this was the first type of antennas that people investigated. And this was mostly wire antennas. So if you look at the early 1900s, we had wire antennas. As you can see, you've got these T-shaped wire antennas used on houses or buildings. You can even see on the Titanic that a similar wire antenna installation on the Titanic. And yeah, they were quite convenient to detect, as you'll see later throughout the course, signals from any direction almost. That's the convenient thing of a wire antenna. But there are some applications that especially became true during World War II, that sometimes you don't necessarily want to detect signals from everywhere, or more importantly, transmit your information everywhere. So especially during war times, we saw a lot of development into waveguide technologies such as horn antennas, and also the reflector antenna came into play there, or let's say started to be implemented. And the reason for these type of horn antennas and reflector antennas, and that is to be more directive. to make sure that you concentrate more of your power in a particular direction, or make a system that's more sensitive to a particular direction, because you don't want the people against you to necessarily be able to capture your information. And really the last part in this, let's say, significant phase in antenna development came in the 1960s. And this was due to the introduction of computational electromagnetic techniques. So we were able to discretize Maxwell's equations and solve this on an element-wise basis. And this allows us to simulate much more complex antenna systems, or let's say structures, how these would radiate electromagnetically. And this is only due to computational electromagnetics that we can really get to this point. And this is also where the patch antenna then also came into existence. And I think for those of you that have worked a little bit with antennas, the patch antenna is actually quite a popular one, still being implemented in, many devices. Laptops or cell phones probably have a few of them. Any most integrated chip antenna arrays or patch antennas, they are still being used all over the place. And that brings us more or less to where we are today, 21st century. And thanks to computational electromagnetics, we can really place antennas everywhere. And this is also what we're striving to do. So what I show you on the left is just the various forms that antennas are being implemented in, from your keyless entry system for your car to all the laptops and cell phones and tablets and your smartwatches that you wear. Our cars are being covered with antennas at the moment. This is just a GPS antenna on a car, but you've got automotive radar that's really becoming very popular now as well. So this is inducing tens or close to hundreds of antennas on your car at the moment. And then of course you've got the entire upper or the other side of the spectrum here, and that's the radio astronomy. Now personally, that's where things get really exciting. As you can see here, this is a 500-meter diameter reflector antenna constructed in China. And the amazing thing with antennas is that this 500-meter diameter antenna actually operates at the same frequency range as the GPS antenna and the keyless entry, as well as the cell phones and the laptops that I show. So you can't really just look at an antenna and think, this is its operating frequency range. It's really, there are multiple ways in which these things can be utilized. So if you look at the near future, I've still put 5G there. I have been putting 5G there for the last, I think, 2-3 years. And you may see our cell phones now show that they've got 5G, and you may even have in your neighborhood if you're lucky. But it's very much still being rolled out and still very much being defined. We only see a certain part of the intended 5G antenna technology at the moment. There's still millimeter wave antennas that will be developed for 5G as well. And this will still be developed and released within the near future. And of course, we want antennas in everything. That's the dream here, the goal, I think, where people keep on referring to your milk carton, telling your fridge that it's running on empty, and your fridge then ordering the milk for you, which we all have been hearing since, I think, since the age of 10 almost. And that's the point where we still want to go towards, is that we want antennas integrated into everyday objects almost. And this also becomes a different type of challenge, because the antennas must become extremely small. They're used in vicinity of various things which obviously influence their performance as well. So these are different types of challenges for especially the next generation of antennas. In this course, we'll mostly focus on antennas for radio astronomy. So that focus will become more apparent during the second session on Wednesday though. So just to give you an overview of that again, as I mentioned, today will be mostly on fundamental antenna parameters, as well as the fundamental antenna elements. So those list of antennas that I showed you in the Mentimeter question, we'll be looking at each one of these antenna elements individually. so that you can get a sense of how they operate and what type of design trade-offs can you make when you are faced with designing such an antenna. Then on Wednesday, we'll look at antenna arrays, or the entire day would actually be allocated to arrays, as well as more focused on aperture arrays for radio astronomy. And in this, I will use an example of the low frequency array and our operative system, which is a focal plane array. So it's an array of antennas mounted on a reflector, or in the focal plane of a reflector antenna. And then lastly, the third day, this will be a software demonstration, and we'll touch on that a bit later. When I give this course, I actually want people to also, well, first of all, be in the same room as me. And secondly, it's always good to have some hands-on experience with the software. So of course, this is not really possible now. Of course, I don't think you can do a software tutorial virtually, unfortunately. So I'll be going through some steps in the electromagnetic design using software of antennas. So I say, for those of you that are really interested in actually designing antennas, I'd recommend the third day. For those of you that just want to get a sense of, okay, what are antennas all about, but you won't necessarily be spending time designing antennas, you may find it a long session, day 3, if I can put it like that. So, of course, it will be recorded, so you're always welcome to look back as well. Okay, so the start. I maybe just give a time now for anyone to ask a question. I can't see your hands if they're raised at the moment or anything like that. So if there's no questions, I don't see anything in the chat, then I'm just going to continue. Okay, we start with fundamental antenna parameters, as it says on the screen. But maybe before we get to that, I first want to remind you of one thing, or one aspect, and that is the following. What I represent here is the coordinate system that we will be working in today. So I think all of you, given the background that I saw, would recognize this as the spherical coordinate system. And I just remind you all of that because I'll be using these field components throughout the course, especially at the start. And it's just so that we're all on the same page. So we know when I say it's E theta, you know where the unit vector is directed to. And if I talk about ER, or the radial field component, we all also know where the radial field component is. So this is just a reminder that if you have an origin somewhere in space that you decided that this is your point of origin, and you have a field radiating from this origin along a radial direction indicated here by R, then that electric field can have an arbitrary polarization. We'll get to polarization later in the course, again, just as a reminder. But it's always convenient to decompose this polarization into 3 orthogonal components. So in the spherical coordinate system, we've got our radial component, and this is directed along the direction of propagation. And then if you were to, at the point where you are solving the field, draw a sphere around that and take a tangential plane to that point, within that tangential plane, you've got 2 orthogonal field components to the radial component, and that we call the theta and the phi components that we can decompose the electric field into. Now, in this course, I just also want to make it clear that we'll be using the definition. Cool, that was not correct. Give me a second. The theta is from the z-axis, and that phi is defined from the x-axis. So this is just for reference. When we talk about the theta angle and the phi angle, please remember that phi is defined from the x-axis and theta is defined from the z-axis. So as I show you, we have the field components, the radial, the theta, and the phi component. And you can always convert these again from a Cartesian coordinate system, where it's defined in terms of the x, y, and z, which is oriented similarly as shown on the axis of this origin. And I think most of you will be familiar with this type of transformation. So I'm not going to elaborate on that here. I'm not going to write the transformation here. If you want to have a look into it, you can Google it, I think, and you can also just find it. It's not really necessary for this coursework. The most important is that for you to be aware how we define theta and phi at the moment, to be aware of these field components, and as well as their directions. So before I move on, just to summarize that again, for example, if theta were to be 0 and phi is equal to 0, then we'll have that the theta component would be directed parallel to the x-axis, and that the phi component would be directed parallel to the y-axis. And of course, the radial component will be collinear with the radial z component. I may get back to you later just to see if everyone caught that, but I think that is clear enough, hopefully. So regarding the fundamental antenna parameters, we'll first look at the field regions around an antenna. And very importantly, we define one specific field region, and this is called the far field. So when we characterize antennas, we always want to characterize an antenna in the far field. And for this, we have certain assumptions that is applicable. So we'll start with that first. And once you have your antenna characterized, or the fields characterized in the far field, you can define certain quantities. And I want to go through the very important quantities, or the most important quantities. And this is called radiation intensity, directivity, gain, and effective area. And you'll be hearing especially gain and effective area a lot when you're working with antennas. So it is always good to know exactly where these definitions come from and why they're important. As I mentioned, we'll look at polarization as well. And then I'll touch on the operating principle of an antenna, again, looking at Maxwell's equations, but more qualitatively. Then we'll look at equivalent networks. So now you've got your antenna designed, but how do you use this when you actually have an amplifier connected to your antenna? How do you implement your antenna in this type of circuit design? And we'll end with a look at two fundamental antenna principles, and that is reciprocity and also Friis Transmission Equation, which is a quite useful quantity or equation to use when you're measuring antennas or the radiation performance of antennas. Then to start, the purpose of an antenna. Why do we make antennas? And yeah, it's actually quite simple, summarized in these 2 points. So the first thing is you have a source, and you'd like, with a certain amount of power, that you'd like to transmit into a certain direction. And to do that efficiently, you require a transmission line. But not only a transmission line, you also require a transition from the transmission line into free space. And you want to make this transition as efficient as possible. And this is what an antenna does. So it guides your wave from whichever transmission line you are currently propagating it on into free space as efficiently as possible. And of course, you want to do that as efficiently as possible. You want to be able to also radiate into a certain direction, but also receive from a certain direction, depending on your application. And that is, in a nutshell, what an antenna is. And these are the two fundamental properties that you'll be keeping in mind when you are designing an antenna element. As I said, there are these two field regions that you can look at, or that we characterize antennas in. So as I show here, you have the area immediately around an antenna element. This is called the reactive near field. So in this region, the field components, the radial, the theta, and the phi component are still very dependent on the distance that you're away from the antenna. So if you're very close to the antenna, they'll have a certain magnitude, but a little bit further from the antenna, they'll be changed quite significantly, as well as the shape around the antenna, of the field distribution around the antenna. And this behavior extends into the radiating near field as well, a little bit less so, but the shape of your field around your antenna is still a function of the radial distance. And it's only at the far field region that the antenna beam pattern really starts to stabilize. So if I were to just illustrate that graphically, let's assume the following, that this antenna element, this is just a schematic of a dipole, a loose schematic, is oriented along the x-axis, and we're looking at the fields propagating along the z-axis. At a certain point, the fields move away from the radiating near field into a region which is the radiating far field. If we are on the radiating near field, we have an E theta component. Well, let's say the y-axis is perpendicularly out of the board. We have a phi component and a radial component along the z-axis. If you were to consider the field distribution at a certain radius, let's call this radius R1, you'll notice a type of, let's just call this an arbitrary field distribution. If you're in the radiating near field at a different distance, you'll see that the shape differs from the initial shape that you saw at a radius closer. And this is the characteristic of the near field. It means that your antenna's field distribution changes as a function of radius. It's only in the radiating far field that your antenna shape really stabilizes and you have your typical beam pattern if you're at a certain radius here. And if you observe it at a radius even further away, it would be unchanged. It would still be identical to the radius a little bit earlier on. The additional part to remember is in the far field, that there's only two orthogonal field components, and that is the theta component and the phi component. We assume that the radial component in the far field reduces to 0. And so this is the most critical part to remember between near field and far field. So if you remember that you only have two field components and no radial field component in the far field, then this is, that is the main message here to take away. The last thing to add here is that this distance that separates the two is equal to 2 diameter squared divided by lambda. So here you have that the diameter is the largest diameter of your antenna element, D. So once your field passes this distance from the source, you can assume this far field approximation. So okay, we now know how to characterize a field in the far field, but I'd like to look into a little bit more detail exactly, okay, how do you, what does this field look like, for example? And if it is in the far field, aside from the fact that you can ignore the radial field component, there are some additional approximations that you can apply to make your life easier when analyzing fields in the far field. And this is illustrated by this figure here. So what I want you to pay attention to, or just to give you an indication of what exactly we're looking at, is we have a source that is in space somewhere, an electrical current source. First of all, we'd like to define the position of this source with respect to a known origin. And that is what is done here. We've placed a known origin there. And what we want to know is, what is the field radiated by the source at a certain observation point, P? So we have these two positions where our source is and our observation point. And this is all with respect to a local origin. So we have these three radial distances. We've got a distance from the origin to the source, denoted by this accent. You also have the distance to the observation point P, which is just this R. And you've got the capital R, which is actually the radial distance from your source to your observation point P. Now, there's some assumptions that you can make here in order to simplify your analysis. So first, what I want to do is just quickly look at how do we define the E field in the far field at this observation point P. So as I just mentioned, we've got our electrical current source in space. And this is a distance R accent from the origin. We've got an observation point P, which is a distance R from the origin, and it's a distance capital R from the source. Now we define our electric field as follows. So the electric field, which is a vector at this observation point P, is equal to this E naught just denotes the polarization and field components, which we can decompose now at the point P. And it's defined by a phase term minus J K R divided by this radial distance. Now, I hope you can all recognize this or have seen this before, but this is the typical expression for an electric field expanding in a spherical nature. So from a point where its origin is, you've got a phase variation defined by e to the power minus jkr, the negative symbol indicating that it's propagating away from the source. And if it's a spherical expansion, the amplitude decreases as 1 over the radius for the electric field as the electric field propagates away from the source. Now, for those of you not too familiar with this, I just have to assume that not all of you are. This value K is called the wave number. And this is defined as 2 pi over lambda. Maybe good if you just write that down for yourself to use at a later stage again. So the way that this phase term works, obviously, is then if, for example, the electromagnetic wave has propagated a distance, say r equals lambda, then this value here, k multiplied by r, just becomes 2 pi in radians. So the wave has then propagated 360 degrees or has undergone a phase shift of 360 degrees across the distance r. Now, if this point P is in the far field, as we've just said, we now know that the polarization of the field is only defined in terms of the theta and phi components, orthogonal to the direction of propagation. The additional assumptions that we can make is the following. In terms of magnitude, we assume that this distance, capital R, is equal to the distance R from the origin. So we assume this point P is far enough that capital R is approximately equal to just R. And we only account for the difference between these two in the phase term. So in the phase term, we say that the distance compensated for is this distance here. So we assume that this signal propagates orthogonal to this radial distance from the origin. And we only account for this projected phase difference, which is equal to this r cos multiplied by psi. So this is just the projection to the point where the source is located onto the radial distance to the observation point. Now, I understand that this may just seem a little bit of a lot of information for almost no purpose at the moment, but I want you to recall this type of analysis when we start looking at antenna arrays, because then this phase compensation comes into play again. So for a single antenna element, you could say, okay, but why don't you just move your origin to that point and then this entire problem is solved. Then R is exactly equal to R and this distance just becomes 0. So you don't bother about that anymore. So I'm going through this analysis again, have a look at it in the notes. And just remember when we get to antenna arrays, we'll be looking at this again. So when we're looking at the distance in terms of phase, this distance R is then equated to, well, let's say the distance R, capital R, is approximated by R minus R hat cos psi. I get a warning that my internet is unstable. I hope everyone can hear me okay still.
Yes, we can hear.
Okay, great. So let's just quickly implement these two approximations that I've now just listed. In the far field, implemented mathematically, we have that in terms of phase, so we compensate for the difference, and in terms of magnitude, I hope you can still see this if I zoom out a bit. There we go. So it's only in terms of phase that we compensate for this difference in distance from the origin and from the source. And in terms of magnitude, we just assume that the source is actually located at the origin. And as I say, we will get back to this at a later stage again, once we're looking at antenna arrays. Before we move on, this is again a equation that I would like you to keep noted down for yourself for later. Just want to move it myself. Okay, so we now have an antenna defined, or we have our far field region defined, and we also know how to describe the electric field at that point, given that it's radiated by a source that is positioned anywhere in space. Now, what can you do with that? So the manner in which we represent this, so I've now only been talking about a single point in space, but you'd like to explain spatially what this looks like. And this is through the use of a radiation pattern. And this is just the IEEE definition for a radiation pattern that I copy here. And just to read through it for you, it's a mathematical or graphical representation of the radiation properties of the antenna as a function of space coordinates. So as I just said, you define the radiation properties spatially. This radiation pattern is determined in the far field region. So this implies that there's no radial component, or we assume it to be negligible. And yeah, we can describe in terms of the directional coordinates, which is either in terms of theta and phi. And the properties that we can plot is power flux density, radiation intensity, field strength, directivity, phase, or polarization. And this will be the quantities that we'll be looking at next, or in a short while, is this radiation intensity, field strength, and directivity especially. And for those of you that have never seen a radiation pattern, this is what one of these would look like. So what you see here is, again, an origin. This is where your antenna is located. And you see this graphical representation showing an increased distance from the origin. And this distance is proportional to the magnitude that you're plotting. So if you're plotting the electric field, if the distance to the surface of this surface is larger in a particular direction than another, it implies that the electric field is larger in that direction than in the other direction. And this is the three-dimensional representation, but we also have two other representations that we plot the radiation patterns in, and that is a polar plot. And I think you can almost recognize what this would be. This is just a cross-sectional cut of your radiation pattern. So your three-dimensional pattern, you can just cut at a certain plane for certain phi angles, or you can also cut it for a certain theta angle if you'd like to. And we can define a number of quantities or values for the radiation pattern. And the terminology for that is, firstly, the main lobe or major lobe. And this is the radiation lobe containing the maximum radiation, so the major lobe. Typically, antennas don't always radiate in only one direction, but there's also a number of minor lobes or side lobes, and these are defined around. And you can also have that the antenna radiates towards the back, then you talk about a back lobe. And we sometimes also number our side lobes. So we'd say it's the first side lobe, second side lobe, third side lobe, etc. Other quantities that are important is the half power beam width. So that's exactly what it says. It's the width at which the electric field, or the power actually, is half of the maximum power. That's our half power beam width. So we just quickly look at the half power beam width. Here you can see that in terms of linear scale, of course, this is a factor of square root of 2. So you sit at 0.7 since it's a half power. So the electric field squared gives you your half power beam width. And you can also plot radiation patterns in logarithmic scale. So then you plot it in decibels. And it's very common to actually rather show your radiation performance in decibel value than in linear scale. So you'll see most of the graphs that we'll look at for the antennas that we design will be in decibel scale. And lastly, as I mentioned, you have the Cartesian graph as well. And here you've got the angles of theta, which here is scanned from the z-axis downwards. We have on the x-axis. So this is our theta angle, for example. And you can read exactly the same quantities again from this graph. So you've got your main lobe, your side lobe levels, your half power beam width, etc. So this is mostly when we've designed an antenna, you go to the radiation pattern and you look, did I receive my half power beam width? What are my side lobe levels? These are the typical quantities that you'll be looking at. What you often come across in radiation patterns thank you. I see Diana just asked about the plus and minus signs. So what you'll see in terms of when you look at the phase in your various lobes is that the phase alternates, and that is what is represented here. So you'll have a certain phase, let's say 0 towards the peak of your main lobe. In the side lobe, you'll have 180-degree phase shift. And this is what's represented. Okay, and let's see, Mohammed asked, at the radiation pattern slide of the 3D schematic, how the electric field or power pattern is getting stronger at larger distances from the source. So yeah, this is just a particular representation. So exactly how the antenna or how the electric field becomes larger in a particular direction, that has to do with the directive nature of the antenna element. And this is exactly what you want to achieve at some point, is to ensure that you, now the word escapes me, that you confine your electric field at the aperture of your antenna in a particular region that will ensure that the most of the energy is in a particular direction in the far field. So, Mohammed, I will try to remember this question and get back to you once we treat this when we look at aperture antennas. Please remind me of that. Now, the last thing I want to add in terms of the different cut planes that you can use to represent the antenna pattern is there are two principal planes, which is called the E plane and the H plane. And you'll very often see that if you look at a paper or something, someone will show you the E-plane radiation pattern. And it's important quantity to know what this E-plane is. And that's just what I want to highlight to you. So if we just consider our favorite dipole antenna again. If we assume a current propagating on this dipole oriented along this direction, And we have a positive polarity here. Oh, that should be a positive. And negative across the port. We have a certain field distribution across like this. I hope all of you can visualize that and see that. And similarly, this field distribution would also be along here. It's actually three-dimensional around the dipole antenna. Other than that, we also know that if we have a current in a conductor, if we follow our right-hand thumb rule, we have a magnetic field that is induced around the antenna. So simply stated, when we talk about the E plane, we talk about the plane that contains the electric field as well as the point of maximum radiation. And this is our E plane cut. So it is the plane that contains the electric field vector. So in terms of, if you look at this type of configuration, you may notice, but the electric field is actually all around along this, this conductor. So you'd be correct that you have an infinite amount of E-plane cuts that you can make. So you'd still want to define that you make an E-plane cut in the, let's say, phi equal to 0 degree direction. However, in terms of the magnetic field, there's only one H-plane cut. So the H-plane would be the plane that contains the magnetic field, as well as the area of, or the point of maximum radiated power. And since there is only one plane containing the magnetic field, and that's just this plane perpendicular to the dipole, this will be our H-plane magnetic field. So I quickly want to hop to Mentimeter just before we take a break, just to see if you've taken the most important parts from this first section. So if you can, oh, I think I pressed twice. Have a look at this question. Okay, so it seems that most people, I think once you notice that the majority says one thing, then your chance is probably that you are correct. Indeed, it is the third option. So I hope that is clear to everyone again. So just a quick reminder about that. A good way to remember that is that if you were to move this radius back to the origin and rotate it back, that the theta component is in line with the x-axis and the phi component is in line or parallel to the y-axis. So indeed you have, in this instance, theta pointing downwards and phi pointing into the screen. I'm moving on to the next question. Great, I said that enough. Yeah, and indeed, I hope you can all see that. It is the radial component that reduces to 0 in the far field. Yeah. So I'm going to move on to the next one. I think you see the more answers coming in, but all following on to radial. Have a quick look at this. Still seeing some answers coming through, so I'm just waiting a bit. Okay, so the majority, if you immediately notice, it's 180 degrees, but then I assume also many of you have probably worked with this before. And since there is still some people that did not immediately see this, I just want to write that down for you to see. I should not have had that. Okay, let's just quickly recap that. So recall that the phase difference is defined by this term here. And to get to the answer, you need to make use of the wave number, k, which is equal to 2 pi over lambda. And the question asked that the wave traveled a distance of lambda over 2. So the phase term, if you look at that, e to the power minus j k r is then equal to e to the power minus j 2 pi over lambda multiplied by lambda over 2, which is just equal to e to the power minus j pi. And this term translates to 180 degrees. So just have a look at that for yourself again, but yeah, the majority of you got that right. I'll just went through it again last time. I think I've been talking quite a bit now, so I am going to get myself something to drink, and I suggest that you do the same, and then we meet one another here again at 20 over, so around 4-minute break, if that's okay. Okay, I hope you're all ready to continue again. So just before the questions, the recap in Mentimeter, we looked at radiation patterns, and we also looked at the fields radiated in the far field. But what I want to look at next are the quantities that you can define, or the radiation quantities that you can define for the antenna. And there's one very important quantity that we need to look at first before we can get to the definitions of gain, for example, that is typically used. And this definition is the radiation intensity. Now, again, I'm assuming that at least the 21 people that have never worked with antennas before, this is the first time that you are seeing the definition of radiation intensity. It is a bit of an arbitrary concept when you first come across it. And again, you may ask, why do I go into these details? But it is essential to understand this in order to understand quantities like gain. So bear with me while I try to run through this. The concept of the radiation intensity is that you want to explain the amount of power that is radiated in a particular direction. So we know that we can define the electric field in a certain direction, but now the question comes, okay, how much power is actually radiated in that direction? And then the first question that you can almost ask is, but okay, around how much of an area should you consider that direction to be? So if I say the antenna is pointing in this direction towards the camera, that point can actually be almost infinitesimally small in space, that direction. So we need to define standardize this direction. And this is done in the terms of this, what we define as a unit solid angle. And what we assume is, if I'm pointing in this direction, I'm actually looking at the surface on a sphere, as indicated by this area here. And that surface has the area of a radius squared, where the radius is the radius of a cone, of which that direction is in the center of that cone. This is the surface that's being spoken of when we say we are looking at the power radiated at a particular angle. If we're in the far field, we've mentioned that the radiation pattern loosens its radial dependence. So the pattern at one radius is exactly the same as the pattern at another radius. And that's convenient because then we can also simplify this definition of solid angle by just ignoring the radius completely and defining everything on a unit sphere. So we make this radius 1. Now, this doesn't mean that we are actually looking at the fields at a 1 meter radius away from the antenna. This is just an approximation we apply to simplify our analysis. So we assume that this is a unit sphere, and we only look at the E field values at that angle when we're defining the radiation intensity. So if you look at that, the radius of this sphere is then unity. We know that the area of a sphere is 4 pi times the radius squared. So in other words, there are 4 pi units of solid angle in on a sphere. And that's just something that will also come in handy a little bit later. I just quickly want to summarize a few things for you here. we now know that the E field in a particular direction, theta and phi, has two field components. So we have E theta in that same direction. I used E theta earlier, but I may swap between E and A theta. Both of these are unit vectors in the theta direction. I sometimes swap between the two. And we also have a phi component. So now we've said we've got this unit solid angle, which is a surface area of 1 on this hypothetical sphere. And we want to calculate the radiation intensity U. This is the amount of power radiated in that angle. We define this as the following. It is the E field squared divided by 2 multiplied by the free space impedance, which is equal to 377 ohms. So that's the free space impedance. Now you might think, okay, this seems a little bit arbitrary, or maybe you'll immediately notice it, but there are actually quite strong parallels. If I were to maybe draw the following to those of you with an engineering background, or maybe just even basic physics. If I were to have a load or resistance, R, and I have a peak voltage V across it, then we all know that the power in that resistance is equal to a half V squared over R. So the radiation intensity is nothing other than that. It's just the power over a load given an E field that is across it. And this is per angle that we define this, where the impedance in this case is free space impedance, which is 377 ohms. This is again one of those equations that I want you to maybe just note down for yourself, which I'm again going to try and copy here. Of the radiation intensity. Now this is useful to know because now we know what is the power radiated for a certain unit solid angle. And if we want to know the total radiated power, all we need to do is integrate over all this units of solid angle. And this is explained there in the expression that you can see. But maybe I'll just also remind you of the following again. If you recall that for a sphere, you have an infinitesimal area that we call dA, which is equal to r squared multiplied by sine theta, d theta, d phi. I hope you all recall this from your calculus back whenever you had it for the last time. Now, for a unit of solid angle, we omit the radial dependence. So we have d omega. This indicates a unit of solid angle is simply sine theta, d theta, d phi. Hence, to solve the total radiated power, P rad, we integrate over all solid angles our radiation intensity, defined per solid angle for this infinitesimal unit of solid angle, or in terms of theta and phi, for phi from 0 to 2 pi, theta from 0 to pi of the radiation intensity in that angle, sine theta. So solving this, if you know your E fields everywhere, you solve your radiation intensities for all those angles, and you can solve the total radiated power for this and on this unit sphere. And I may also suggest that you maybe quickly note this one down. Oh, that came out very large. Not to do that. I may write it down in a second. So if you note this one down for yourself, because I'd like you to quickly use this, and that is, if you look at this problem here, what is the total radiated power of an isotropic radiating element? So firstly, you may need to know what I mean with this word isotropic. Now, what this refers to is an element radiating equally in all directions. So it radiates a perfect sphere, meaning that it has the same radiation intensity at all angles. So as I show here, U at every angle is just a constant U naught. So given that, I'd like you just calculate the total radiated power. And I think I can show this on Mentimeter. If you quickly have a look on Mentimeter, you should see it now. Okay, I see some of you attempting it. Some more. We're nearly halfway through everyone having attempted it. So I'll maybe wait for a couple more. Right, so I think we're there. We're nearly halfway of people answered. It's a bit of a distribution. So I may just to show you what the result looks like now. The majority of you had correctly identified that there is actually 4 pi solid angles in a sphere. So that's a quick way to, if you just remember that, then you immediately know the answer without having to worry about the integral. but yeah, it's a simple matter of solving the integral to get to the total radiated power. So firstly, for an isotropic radiator, if you're looking at an isotropic, we know that U0 is the same for all angles. So we can take it out of the integral. And then it's just a matter of the integral of sine is minus cos, integrated from 0 to pi. And we've got phi, which is integrated from 0 to 2 pi. So this results to 2 pi. If we calculate this, we get the factor 2. And the answer is 4 pi U0. And this is a very important result that we will be using in our future definitions as well. So the total power radiated by an isotropic radiator is 4 pi multiplied by the radiation intensity of that radiator. I've lost the chat, so just give me a moment. Okay, I can still see the chat. And this is exactly where we use it now, is in this definition of directivity. So directivity, this is the IEEE definition, and this is the only way that you could really explain it. So I have to show it this way. It is the ratio of the radiation intensity in a given direction from to the antenna's radiation intensity averaged over all directions. So all radiated isotropically. So just to repeat that again, you look at the radiation intensity in a particular direction, and you compare that to the radiation intensity that would have been radiated if all the power radiated by the antenna was radiated isotropically. So if we can write that down, my computer is slowing down a little bit, it seems. Okay, we've got movement again. What we are looking at here is, let's say we have an antenna that has radiated this type of radiation pattern. We have our side lobes, back lobe. And what we're interested in is the directivity at this particular point there. So we know what the radiation intensity then is at this point. Let's just call it P for now again. That's the point P. So the directivity at the point P is defined as the radiation intensity at the point P divided by the radiation intensity that would have been radiated isotropically. Well, the question is, how do we obtain this? How do we obtain the isotropically radiated radiation intensity of this antenna? Well, the simple way is we first integrate the radiation intensity of the antenna to solve the total radiated power. So we first solve P rad. Once we have that, we know that P rad is equal to 4 pi multiplied by this isotropically radiated power. So we can define an equivalent isotropically radiated power of this antenna. So the power averaged over all angles. This would then be U0 for that specific antenna. So therefore we can replace this U0. We know that U0 is equal to total radiated power divided by 4 pi. Therefore the directivity is the radiation intensity at the point divided by P rad divided by 4 pi. Or ultimately, in the way that it is typically written, it's 4 pi multiplied by the radiation intensity at point P divided by the total radiated power. This is our first definition, directivity. And if we just think about that term, it explains the directive nature of the antenna. So if you take the power that has been radiated by the antenna and you distribute that evenly everywhere, isotropically, and you compare it to the actual power radiated in a particular direction, then you have a sense of how directive this antenna element is. Important thing is to note is that it's with reference to the total radiated power. That's the main definition for directivity. Moving to our next definition, the gain. So we now have to find directivity. And now we need, well, we go on to our following, which is often used as well, is the gain of the antenna. Now, if we look at that definition, again, I'm just using the IEEE definitions. That is, it's the ratio of the intensity, or the radiation intensity, in a given direction to the radiation intensity that would be obtained if the power accepted by the antenna were radiated isotropically. So that's the very subtle difference between radiation and gain, directivity, sorry, and gain. Directivity is in terms of the power radiated by the antenna, and gain is in terms of the power accepted by the antenna. So if we were to illustrate this, consider the following schematic. Let's assume that we have a source. Oh, well, I could actually disconnect the generator load as well to this. Let's do that. And then we're connected to an antenna. So here we've got a generator, source impedance, and the antenna. So this antenna radiates the radiated power. And at this point here, we've got our accepted power by the antenna. What do you think is the difference between the two? How are the radiated power and the input power connected to one another? Or let's say, what would influence the accepted power to cause it to be different to the radiated power? Anyone want to take a guess and type it in the chat? No? Okay, so Mohammed says that P in is greater than P out. Yeah, correct. Pierre says it's a Z0 impedance. That comes next, so not quite yet. So indeed, this will play an effect, but at the moment we're only looking at P in. So Pierce will get back to that Next. Yeah, Nestor says maybe P rad is P in, where E is some energy loss. And that's exactly what it is, that energy loss. And this we call some type of efficiency that we have, the conductive or dielectric efficiencies. So our antenna is made of some material, and this is never ideal. And you always have some type of conduction losses or dielectric losses, depending how you realize the antenna. And this results that the radiated power is actually equal to this conductant losses multiplied by the input power. And this conduction losses is always obviously smaller or equal to 1, but it's actually never equal to 1 because there's always some losses, the conductive losses. So if we go back to the definition of gain, it says it's in terms of the input power. So if we were to write that down, trying to find a nice spot to do that. We have the gain of the antenna, again defined in a certain direction, is equal to the radiation intensity in that direction divided by, well, we've multiplied by 4 pi because we know that should be done from the definition of directivity, if the accepted power is radiated isotropically. But we just said that P rad is equal to P in multiplied by the conduction losses or the dielectric losses. If we just write this in terms of P in, you'll notice that the gain is equal to the conductive and dielectric losses multiplied by 4 pi u in the particular direction again, divided by P rad. And this is just equal to, again, the conduction losses multiplied by the directivity. Because directivity is again defined in terms of the total radiated power. And that's the difference between gain and directivity, is the one accounts for losses in your system and the other accounts, assumes just the total radiated power, so it does not take losses into account. Or it is inherently always already taken into account due to the fact that it only considers the radiated power. There's one little side note that I want to mention here, and that is that directivity is measured when you talk about the decibel quantity of directivity only now, you see that it is measured in dBi. And this I stands for the reference to an isotropic radiator. If you talk about gain, very important, a gain especially that has included some loss, then we talk about dB. You'd sometimes see that people would refer to gain as a dBi as well, but strictly speaking, that should be directivity. The only reason why you can talk about gain as a dBi implies that the gain is actually the directivity being shown or no losses are taken into account. So that's just something to bear in mind. But the dBi for directivity is a common convention that you'll see a lot in antenna publications. Lastly, and this is to get to, I think it was Pierce that asked, what about the impedance? And that's the third definition, and that's called realized gain. So the realized gain is defined in terms of the gain, but it takes mismatch into account. So we know the antenna has a certain impedance, which I'll just draw here as a dotted line. Oh, that's a terrible rectangle. Try again. So we have a certain impedance, Z aunt, which we'll get back to shortly. And of course, we have a reflection coefficient. So some of the power, not all the power, is accepted by the antenna, and we have a reflection coefficient gamma. And this is where the definition of realized gain comes into play, that the realized gain, G, which I'll just denote here with an R, again defined at a certain angle, is equal to the mismatch efficiency multiplied by the gain of the antenna, where this mismatch factor or efficiency is just equal to 1 minus the magnitude of the reflection coefficient squared. And so Piers, I hope that answers your questions with regards to the impedance. That is only when you talk about the realized gain do you take into account the source. So all other references are from the port of the antenna onwards, accepting or working with the power accepted by the antenna, and then either assuming losses or not. Now, up until now, I've just been mentioning antennas that are radiating. So we're only looking at the gain transmitted and the directivity transmitted, and I talk about the radiation intensity transmitted in a certain direction. But obviously, antennas don't always transmit, they receive as well. And there's a very handy definition that we use in the situation when we're talking about receiving antennas, and that is called the effective area. Now, I will again suggest that this equation you also write down, because we will be using it at a later stage again. So please note this one down. But just to explain to you what this effective area is and how it's used. Let's consider an antenna element. This will be a receiving antenna element. And this element is connected to some type of load. So with this load, I am representing an entire receiver, just to simplify things for the moment. And this has a certain impedance, ZL, load impedance. And we have an antenna, which we say has a certain effective area. Now, if we have an incident signal in the form of a plane wave incident on this antenna element, this has a certain flux density. So this called W incident. And this flux density is in terms of watt per square meter. The useful tool, for the lack of a better word at the moment, of effective area is that we can define a received power in this load. So the power received by this load is equal to the effective area multiplied by this incident flux density that we have. So obviously effective area is in units of meter squared. So we have watt per meter squared incident on the antenna multiplied by the effective area of the antenna gives us the power that is in the load. Very important is that we are assuming that this load is conjugately matched to the antenna. And then this applies. And that's a really handy thing of having a definition such as the effective area. And the way that we define effective area or solve effective area, and this is the equation that I'd ask you to just note down for yourself, is again, it has a theta and phi dependence because we define it per angle. Effective area is equal to, I always get confused with this, I think I have it right, lambda squared divided by 4 pi multiplied by the gain. Just want to confirm that I did not send you down the wrong. Indeed. So lambda squared over 4 pi multiplied by the gain, that gives you your effective area. And as I say, just note that one down for yourself. We will get back to that in a while. Of course, you can now ask, okay, but why not just use the physical area of the antenna? It's handy to have this relation to gain, because sometimes an antenna's collection area can appear larger than its physical area. For example, in the form of a dipole, we actually just have a thin wire. It can have a relatively large effective area. But once you start looking at aperture antennas, you'll notice that your effective area can actually never really reach your physical aperture of your antenna. It always approaches that at the best. And the way that this is related for aperture antennas is that this effective area is equal to the aperture efficiency multiplied by the physical area. And this is a quantity often used in reflector antennas, is this aperture efficiency. And we'll get back to this later. So you can solve the aperture efficiency of an antenna, a reflector antenna, if you know the physical area and you know, well, the gain of the antenna, because that way you can solve the effective area. And at the end of, hopefully by the end of today, we'll be running through an example like this. That's nearly the end of all the definitions. Now, I said this first part of the course is, I know it's terrible. It's just this definition upon definition upon definition upon definition. And you may be asking, what is the point of all of this? You probably are, but you have to see this once. So go back in the notes, look at this. Thank you, Mohammed. We're not there yet. Once we get to aperture antennas, we'll get back to this as to how the electric field can be stronger in one area than in another, if that's okay. So yeah, this is for my summary, the most important parameters that you need to know, and you will be using these now, as I told you, to write this down and write this down and write this down. We'll be using these values when we start designing antennas. Before we get to that though, I need to touch on one topic, and we almost started with that when I said we talked about polarization, or at least decomposing a certain polarized field into its orthogonal components in a spherical coordinate system. So I just quickly want to remind you all that waves are polarized. They are always polarized, because we have to define them in terms of some reference. And of course, polarization is extremely important, because if you have one antenna that's polarized, let's say vertically, and you have another antenna that's polarized horizontally, you are not going to couple any power from the one into the other. They need to be copolarized. So it is very important to take polarization into account when you design antennas. And there are three types of polarization. The one is linear polarization. So in that sense, the wave is just, as it says, polarized linearly, for the lack of a better way to describe it. And then you have circular polarization, which means that the polarization state actually rotates in a circular manner. And I'll show you quickly in an animation how that is achieved. And in addition to that, you've got elliptical polarization, which in essence is a circular polarization. The only difference is the field components are not exactly equal to one another. So that you almost have an ellipse instead of a perfect circle. Or it can be that the phases are not exactly 90 degrees apart. But the animation will show you this as well. So let me quickly start that animation for you. Okay, so first of all, what you see here is the two orthogonal field components. You've got the EZ component and the EY component in this case, but this could be theta and phi as well. And we'll see the two field components, or the wave decompose into its two field components, and then ultimately the resulting polarization state that is achieved. So for linear polarization, as it states, these field components are in phase. They don't have to be equal, but they are in phase. So they're maximum at the same time and a minimum at the same time. And this results in this green linear polarization state. So this is actually the orientation of the electric field as it propagates through space. As you can see, it always oscillates between a maximum and a minimum that you can decompose into these two field components. And again, the magnitudes can change, or the magnitudes of the two field components doesn't have to be aligned. That just defines a polarization angle. So what you saw now is once you shift one of the field components phase with 90 degrees, so that's what just happened. The red field component was delayed by 90 degrees. So it is a maximum when the X component is a minimum. Then you get circular polarization. And the resulting field will show you why it's called circular. So you see, when the one's a maximum, the other field component is a minimum. And if you now look at the resulting polarization state, it rotates as the wave propagates. Now we have two types of circular polarization. The one is right-hand circular and the other is left-hand circular. So I'm going to pause it, or more or less here. And the way that you can define what state of polarization this is, right or left-hand circular, is if you point your thumb in the direction of propagation, so in this case it'd be into the screen, then your fingers curl into the direction of propagation, of polarization. So in this case, it's clockwise rotation. So we have a right-hand circular, and it would have been left-hand circular if the rotation had been other way around. And that's just in a very brief summary what polarization is. You'll see in the notes, I've got some descriptions for you, additional descriptions that you can have a read through that explains these polarization states for you. I just quickly want to find the chat again. There we go. Okay, I suggest another 5-minute break again, and then we continue. So maybe we make it up to 3:10 or 10 past, whichever hour it is where you're at the moment. So we take a short break again. Okay, I hope all of you are back again. We're now moving closer towards the point of actually looking at some antenna types. But before we get there, I'd just like to start with a description of, very qualitatively, a dipole antenna in free space. I saw as well when you said your experience with antennas, the majority of you that have looked at that antennas have considered the dipole antenna, and it is just a nice example to start with. And then to get to that point, you have to at least start with a description of Maxwell's equations again. And well, as I mentioned, Maxwell's equation relates the electric and magnetic fields to the electric and a non-physical magnetic current, as well as the electric and non-physical magnetic charges. Well, maybe not quite. But in essence, before we continue with that, I just want to remind you the one thing. Where is it? Yeah. Just recall that the magnetic flux, D, not directivity, magnetic flux in this case, is equal to the permittivity of the medium multiplied by the electric field. And similarly, the magnetic flux is just related by the permeability multiplied by the magnetic field. So in these quantities, if you see magnetic flux and the electric flux, then it's actually just, in essence, the electric field and magnetic field, although the permeability and permittivity is taken into account there. So I assume all of you have actually done this type of calculus, but just a reminder again, the curl and the divergence represented here. So the curl of the electric field here explains spatially how the electric field rotates around a certain point. So that's what is expressed here by this curl of the electric field. And similarly for the magnetic field. And the divergence is how it explains the flow from a particular point. So through a certain surface around a point. So if you imagine a charge just just radiating a field outwards, it explains this flow through the surface surrounding this point. So to explain how this works qualitatively, what I want you to imagine is, well, free space, nothing, and then suddenly a current appears in the middle, let's say the origin. And what we can see from Maxwell's equation is, that should not have happened. There we go. Is that if we have a current density, an electrical current source, this is represented by J, that appears, we know that we get a magnetic field around it. So it shows here that you have a rotating magnetic field around the current. Now I want you to imagine that this source is not static, but it actually oscillates. So it changes in time as it oscillates at its particular frequency. So what do you think happens to the magnetic field around that? This also changes in time along with the manner in which the current changes. And if you look at the expression for explaining a rotation in electric field, if there is a time varying magnetic flux, which is related to the magnetic field, it creates a rotation in the electric field. So you've got this time varying current source that creates a time varying magnetic field. And the time varying magnetic field creating a rotating electric field again. But of course, as the original current creating this is still changing, it results in a changing electric field again. And in the absence of an electric current, a time varying electric field creates a magnetic field again. And this just repeats itself as long as the current in the middle continues to change in time. You've got time-varying magnetic fields creating electric fields, and time-varying electric fields creating magnetic fields, and yeah, the wave propagates until the current source stops. So the conclusion with all of this is that I want you to take home. You need a current source. The moment that you can define the current on a structure, then you can solve the fields. And this is especially true for wire antennas. So to get to that point is of defining the current on a linear wire antenna. I'd like to take this example of an electric dipole. So what I want you to imagine here, what is represented here, is a twin axial transmission line. So this is just a transmission line, for example, connected to some type of source on the one end and open-ended on the other end. Now, what I hope that you would know and recognize is that, of course, if this is an open-ended transmission line, so the current is 0 at the ends. But given the fact that it's open-ended, you get standing waves on this current, or on this transmission line. Now, if you were to visualize bending open this transmission line at a certain distance, this sinusoidal current distribution on this transmission line doesn't cease to exist. It's a very, yeah, if you were to imagine this, if someone asked you, here's a dipole antenna, what's the current on it? That's not a very simple thing to just explain that it is sinusoidal. This is almost one of the best ways to visualize that it could be sinusoidal, is to see it as an open-ended transmission line, which we know has standing wave ratios on it, or standing waves on it. And if you bend it open, that same sinusoidal nature is maintained on the dipole antenna. And if you were to measure this in a lab, if you have a lab around and you've got a dipole antenna and a current probe, I would really recommend that you do this. You actually can measure this sinusoidal distribution on the dipole antenna and see indeed that if you take the current probe and slide it along the length of the dipole, you'll see that the current is indeed approaches 0 at the end and becomes a maximum in the center if it is at a half wavelength. And that's the point that I want to get to next. Is I hope you can see from this representation here that this standing wave is a maximum at a quarter wavelength from the open circuit. So if you were to bend this dipole open at a quarter wavelength distance, you have a result of half a wavelength. And at that point, the current is a maximum in the center. Then this maximum point meets that of the opposing arm. And that in principle is the current distribution on a half wavelength dipole. If the dipole is half lambda, you have this half sinusoidal current distribution where it is 0 at the ends and a maximum in the middle. So I again want to ask you to quickly have a look at Mentimeter. If you okay, I see it seems to have stabilized. Well, there's one or two more coming in. I see a number of falses coming through. So just to give you an overview of the results. I think from the majority that you can see here that, okay, indeed, this is true. So just to recap, the trick here is lossless. So as we said in the definition for directivity, that, or definition for gain, I apologize. The gain is equal to the conduction losses multiplied by the directivity. So if there's no conductive losses, this becomes 1, and the gain and the directivity of an antenna is exactly equal to one another. If we look at the next question. Just a reminder to choose 2 correct answers. See some people's, yeah, there's still some answers coming through. Right, so it seems to stabilize. See some people still thinking, but let's have a look. So the majority of you agree that in theta 90 degrees, we indeed have a maximum, but yeah, it seems odd that the second maximum is it's still in doubt. So let's quickly have a look at this figure. Now, very correctly, the electric field radiated is proportional to, let's say, the current that created it. So in the position where the current is a maximum, indeed, you can expect maximum power radiated in that direction. So theta equals to 90, indeed. But remember, this field oscillates around this point. So the maximum rotates continuously around the center. So you could imagine it oscillating as a standing wave around this dipole. So the maximum is always towards either 90 or theta equal to 270 degrees. Along 0 degrees or 180 degrees, the current is always 0. There's no current at the end. So conversely, or not actually conversely, because of this, the fields radiated in these directions are also 0. So indeed, the correct answers were theta 270 degrees and theta 90 degrees. And to show you graphically what that looks like, this is what we call an omnidirectional radiation pattern. And this is the radiation pattern of a half-wave dipole antenna in free space. Now, Mohammed, I guess I could come back to your question where you asked why is the power more in one direction than another? This is due to the current distribution on the dipole. So you have at a position where there's zero current, implying that in a certain direction, there'll almost be zero power radiated. And if you have a maximum in a certain direction, you have maximum power radiated towards that point. And the same applies for aperture antennas in terms of field distribution, which we'll get to hopefully by today, we'll see. So this characteristic, what you see here is you should imagine that you've got this dipole antenna right along the center of this null that you can see here. So this is the axis of the dipole antenna. And towards 90 degrees or 270 degrees, for all angles of phi around it, you have this maximum. Because remember, it's not just along a line that the current runs, but it runs on the surface of this dipole. So you've got a surface current distribution that is shown in this graph here, actually, not just along one line. And it's maximum power radiated all along around theta equals 90 or 270 degrees. And if you, of course, if you were to take a cross-sectional cut in the H-plane here, so the H-plane would be dissecting the dipole here, then you've got this just almost perfect circular ring for the radiation pattern. Now, in terms of directivity, the directivity of a dipole is around 2.15 dB. This is just an arbitrary value for you, but it's not a lot, in other words, because as you can see, it's, well, it's not quite isotropic, but it's only a small part where it doesn't radiate. So most of its power is still radiated across an entire sphere. So Mohammed, you're asking about the square inverse law of intensity. So now you're talking about if you're moving away in a radial distance. Is that what you mean? Yeah, so remember we're in the far field here. So we're assuming that the field is not related anymore to a radial distance at all. So the magnitude you're seeing here from the center is just a value of the field intensity. So we're ignoring radial distance here and have assumed that we're showing the data on a sphere of unit radius. This is the definition of the electric, or no, this is actually the gain, we can call it like that. Because also remember that this quantity is normalized to the total radiated power of that antenna. So it is normalized to its own amount of power. So we do not look at it as a radial dependence anymore. I hope that makes sense to you. Okay. So I want to write down a couple more things for you regarding this dipole antenna. And these are just nice quantities to know. I don't know if you... This is not working as planned. Okay, there we go. So first of all, for a dipole antenna in free space, a half wavelength dipole, if I just type that down for you. We have that the impedance of the dipole, Z for the dipole, is approximately equal to 73 ohms plus J, I think it's 42, yeah, 42.5. This is approximate. So if your dipole is half wavelength in length, this is the impedance of the dipole. Now, what I want you to notice is this is an inductive part of the dipole. So what we typically do is we create a dipole that is slightly shorter in order to reduce the inductance. So we want to take this part, so Jx of the antenna, we want to bring that to 0. It doesn't always have to be like that, but if you want to match it to a certain transmission line with a characteristic impedance, typically of 50 ohms or 70 ohms, then you want this imaginary part to approach 0. And when this happens, when Jx approaches 0, we call that the resonant frequency or resonance. So when the imaginary part of the antenna impedance approaches 0, we say that that's the resonant frequency or the first resonant frequency of the antenna. And to achieve resonance with a dipole antenna, so as I now said that the length should be equal to lambda over 2. In practice, what you have is that it's closer to 0.46 to 0.48 lambda. And the reason why we make it slightly shorter is to reduce this inductance. Because remember that an inductor is actually just a piece of transmission line. Or can be represented, let's say rather reverse that, a transmission line can just be represented as an inductance as well. So by removing a section of transmission line, we actually reduce this inductance. And then you have that Z of the dipole is then equal to only 73 ohms. And that's something to aim for. What we generally aim for when designing antennas is to reduce this imaginary component. Of course, if you know what type of load you're designing your antenna for, then you can design your antenna to be conjugately matched to that load as well. So that's just a little side note to take into account. So let's have a look at this equivalent circuit then of an antenna. So I've now spoken about the impedance of the antenna. And in terms of an equivalent circuit of an antenna, that is exactly all it is. It is just an impedance. It's actually very simple to include in your circuit models. So as I show here, that if you have some generator with an impedance, and you connect this to an antenna that's radiating an electromagnetic wave, then you can represent this entire circuit as your voltage generator and the load, or let's say the source impedance, and then the load impedance of your antenna, where you'll notice that there's two components to the antenna impedance. It's got a real part and an imaginary part. So as I just mentioned, for the dipole, this imaginary part is around 42 ohms for the half wavelength. But we actually want to reduce that so that we only have a real part. Now I want to zoom into only the real part of the antenna impedance. So we said we have the impedance of an antenna, which is equal to the real part of the antenna plus an imaginary part. Now the real part of the antenna has two components, and the one is what we just call the loss. So this is conduction losses or dielectric losses of the antenna itself. It's just a standard form of loss energy conversion. But there's a different part that contributes to this, and this is the radiation resistance. And the radiation resistance of the antenna is defined by the total radiated power of the antenna. So this may sound a little bit strange, but let me try and explain that to you. So if we have an antenna element that we've now just modeled as a resistance, and we've got a certain current flowing through it. Let's just assume that this antenna is lossless, so R loss is 0. So all we have here is R rad. This is the total real part of the antenna, R rad. We've now seen how we can solve the total radiated power of an antenna. Or let's backtrack a little bit. Let's ignore this for a fact, and that this is an antenna. And all we want to calculate is the power in this load. Then we know that the power in that load is equal to half I squared R rad. That's a standard circuit theory. This is assuming that this is the peak current, and we're taking the RMS value here. And this is exactly the way that the radiation resistance is defined. If we know the total radiated power of the antenna, then we can solve the radiation resistance as there's a square missing. I see, yes, indeed, Colin. That is indeed on a completely different topic. The 73 greeting is indeed, I think, related to the ham radio greeting for those of you that are ham radio enthusiasts. That would be the impedance of the dipole. So back to the radiation resistance then. I hope this is quite clear to you how this quantity is defined. It is to give a sense of how much power is radiated. And this has to come from a real load. That's the only way that we can dissipate power in the antenna. So the way that we model this power dissipated in terms of a radiated power is by this real resistance called the radiation resistance. So if you know the current on the antenna, or let's the peak current on the antenna, and you know the electric field radiated by the antenna, you can solve the radiation intensity from the electric field. You can integrate the radiation intensity to get the total radiated power. And you can divide that by the current squared again. And you know what the radiation resistance of your antenna element is. This was now in transmit mode, but if you were to just reverse things and observe this antenna in receiving mode, then, yeah, well, the circuit doesn't really change. The only thing that changes is instead of the fact that you have a generator voltage on this side, you only have a load on this side. And the signal induced at the antenna port is now indicated on the antenna side. So you've got your signal on the side of the antenna induced, and you've got still exactly the same impedance, the radiation resistance and the load or the loss resistance and the imaginary part of your impedance, of your antenna's impedance that you take into account. And of course, if you want to have maximum power transfer here, you want to have these two conjugately matched again, this time to your load impedance. Now, I don't know if some of you found it confusing what I just did there. On the one hand, I say, so antenna's transmitting, and this is our impedance, and now antenna's receiving, and it's exactly the same impedance. And you just do that, and that's the way it should be. This is something that's very fundamental to antennas, and it's a property that we now really take for granted, but it's something that you should be aware of. And this is called reciprocity. Reciprocity, let's try again. And yeah, stated there it is that the radiation pattern of an antenna in receiving mode is identical to the radiation pattern of the antenna in transmitting mode. And it's thanks to this principle of reciprocity that we can just talk about an antenna. Even a receiving antenna, you talk about its gain in transmit mode because there's really no difference in it. Once you know how it transmits, you know how it receives because they're all the same thing. So just to maybe play this thought experiment with you. Imagine you had, as shown here, two antennas, identical antennas to one another. And in the one situation, you keep the one antenna fixed, as it's shown here, and you rotate the other antenna around it. And the antenna that is fixed, you are receiving from, and the antenna that you're rotating, you're transmitting from. So let's just say for each of these angles, I now plot the voltage or the power I receive by this receiving antenna. So I'll just do this in Cartesian coordinates. So along this axis, I've got theta scanning. So this is, let's call this theta 0. But let's say that power that I'm receiving is resembled by something like this. This is now as I am rotating my transmit antenna around my receive antenna. For each of these angles, this is the signal that I measure. Now let's say I reverse that. So remember I had the transmit one rotating like this. Now I keep my transmit stable and I switch it to receiving. At the same time, my previous receive antenna, I'm now making a transmitter. And all I'm doing is I'm rotating it around its own axis. And I'm comparing the signal that I'm receiving now with my previous transmit antenna. If you were to plot that received power, you'll notice that they line up exactly on one another. So these two curves will actually just, well, more exactly than I can draw it, follow one another. And it's this way, through this experiment, that it is proven that antenna elements transmit and receive in exactly the same way. Of course, there's a lot of mathematical elaboration on all of this to prove it to you, but empirically, it can just be shown like this. So now I've talked about just measuring antenna patterns as well, and it is this manner, as I just illustrated, by antennas being rotated around one another. That's exactly how we do it in practice, how we measure antenna elements in an anechoic chamber. And there's this very useful expression, which is called Friis Transmission Equation, that we use to relate the received power to the transmitted power between two antenna elements. Now, this is the Friis Transmission Equation that I show here. And maybe if you first look at it, you think, okay, I don't even want to look at this. It's just too messy. But I quickly want to run you through it. It's actually not as, let's say, not as involved as it looks. So if you're seeing it for the first time. So the purpose of Friis Transmission Equation is the following, that if you have a generator, let's say it has a certain load connected to an antenna, and you have another antenna connected to a detector, which I'll just represent here by a load again. So what we want to know is the power received on this side, the power received versus the power transmitted. And the first thing that we need to do then is to just follow the signal path. So we have power transmitted. So I just like to follow mentally what happens to this power. It enters the antenna. So the very first thing that happens when it enters the antenna is, of course, this antenna is mismatched. It's not matched to this transmission line. So we have a reflection coefficient on the transmitter side. So we have the power received. Oh no, let's start. Yeah, the power received, yeah, is equal to the power transmitted multiplied by mismatch efficiency, which we said in the beginning is 1 times gamma RT squared. So now we're at this level already. We've accounted for mismatch efficiency. There can also be conduction losses in the antenna, which we know from the definition of gain. So it goes through some conduction losses in the antenna. So now we're at least at the antenna point where power can be radiated in a certain direction. So we have a directivity of the transmit antenna in a certain direction, theta t, phi t. We have the directivity of the transmitter in a direction, theta t, phi t, where these directions is directed towards the receiver. These antennas are separated by a distance, lambda, oh, beg your pardon. Let's just call it the distance r. To account for the free space loss due to just this, remember this, the signals expand spherically. So there is a loss in signal magnitude just because that physically happens. And that's called the free space loss factor. And that free space loss, so say free space loss, is equal to, oh, I just have to make sure I write it down correctly. This is the free space loss. So that term is accounted for as well. So now the signal has transmitted from this antenna up to this point here. Oh. Then we have the same just in reverse again because of reciprocity. We can define this. So instead of the antenna being now transmitted, we have the directivity of the received antenna that multiplies the signal. Receive antenna phi. Again, this one is slightly different in orientation. They don't have to be pointed at one another at the same angles. So we have the directivity of the receive antenna. Now the signal is at least at the antenna or in the antenna, let's say. But again, we've got conduction losses of the receive antenna. And then lastly, we again have a mismatch, which is on this side due to the receive antenna. So we account for the mismatch efficiency. And that in essence is exactly what is written here. So we have conduction losses on both sides. We've got mismatch losses on both sides. Free space impedance or free space loss that is accounted for. The directivity of both signals that amplify the signal. And the last term here is a polarization mismatch term. So that's just a dot product between the two polarizations. And if they are perfectly aligned with one another, that just becomes unity or one. And if they're cross-polarized, you can't really see the black pen. If they're cross-polarized, then of course, this entire term goes to zero or nearly zero, meaning you receive no power. Now I notice we have 10 minutes left in this session. This has gone far too fast. So it's a good thing we have 3 days. Because I want you to actually give this an attempt quickly. So if you can open Mentimeter, I think I've given you 7 minutes for this, but maybe I should give you a little bit more. will show it to you now. Okay, it seems that I'm just quickly going to restart it. It seems something strange is happening at the moment. Okay, so I see everyone is there. I hope this will happen once I press enter. Okay, so see if you can solve this. You have, I think, 7 minutes. No, you have 10 minutes actually to solve this. And I will put in the expression for you again. still see some answers coming in, so we just wait for the clock to tick away. So while the rest of you are still solving it, let's just see. Hopefully everyone got for free space path loss. That should actually be an L, but yeah. I hope everyone got a value like minus 34.71 dB. Just bear in mind, this is not the receive power, this is the path loss. So this component here. Carmen, just to get back to your question, I see you asked, is the free space loss the same in the near and the far field? Now, it's a good thing I had 10 minutes to think about this. I'm cautious to just answer that and say yes. The reason for that is this expression that we see here, or Friis Transmission Equation, assumes that your antennas are in the far field. So then you have the far field approximations that apply, and hence you can assume a spherical expansion of your field. And therefore you can use this free space loss factor, assuming that. A completely different set, or measurement expressions apply when you're trying to characterize antennas in the near field. So you can do that. You can measure the near field, but then you'd have to apply a Fourier transform to the near field distribution to get to the far field. So I'm not 100% sure, and their radial distance does apply. I would say in this instance, this assumes definitely the far field. That's the safest answer I can give you at this moment. But let's have a look at the results. So I see we have quite a number of different answers. Yeah, we had people saying minus 35.5, correct. You could have said this in any other various ways. Okay, I see some people have gotten quite some different results here. I think someone potentially did this in linear scale. Someone missed close enough, but missed, I think it could be the loss in the actual conductor that had been missing here. So I know we are technically over time, but if you don't mind, then maybe we quickly run through this and then I will call it a day. So first of all, let's see if I can do this. We have an input power of minus 20 dBm. So we have a transmitted power of minus 20 dBm. We have a gain of the transmit antenna equal to 1.2 dBi. Gain of the receive antenna equal to 6 dBi. The free space loss, so the loss factor, as I just showed you, was equal to lambda over 4 pi multiplied by the distance between them squared. Lambda is just solved as the speed of light divided by the frequency range. And if you calculate this and convert it to, remember to 10 log that answer, because you've already squared it here, then you get minus 34.7 decibels. So in the end, if you want to calculate, oh, don't forget the loss of the cable here. Loss of the cable is equal to minus 6. So we said that the received power is equal to the transmit power multiplied by the gain of the transmit antenna. Obviously, we have that loss in the cable that actually comes first, multiplied by the free space loss factor multiplied by the gain of the received antenna. Or in logarithmic scale, we can just sum all these things. So power of the transmit plus the loss of the cable plus the gain of the transmit antenna plus the gain of the receive antenna plus free space loss. And if you just calculate the sum, all you get 20. 20 minus 6 plus 1.2 plus 6 minus 34.7. And this gives you the answer of minus 53.5 dBm. So have a look if you can get to that again. As I say, I'll be sharing the notes with you after this presentation, or after that really then brings me to a close for today. I will be honest, I actually hope that we get to a fundamental antenna elements today, because it's really where it gets very exciting. But I hope going a little bit slower through this first part of the course has paid off for you, that you at least have heard the same thing multiple times, and hopefully it sinks in like that. So I will end it here. We're 10 minutes late. I apologize for that. And then tomorrow we will really start looking at antennas. So dipole antennas, patch antennas, horn antennas, reflectors.